Good morning. Today we will continue with our discussion on angular momentum a little bit and then move on to a new topic, that is the gravitation and Kepler problem. Now last time, remember, what we have seen was a conservation law which came out of a symmetry in our system. And the conservation that we have seen was the conservation of angular momentum. Does any of you feel that angular momentum is conserved? Not here, probably, but can you do an experiment in which you will demonstrate yourself that angular momentum is indeed constant? Yes, you can. For that, you need to remember few important points. Now, linear momentum is what? What is linear momentum? What is the dependence of linear momentum? It has mass, and it has the linear speed of the object. If you put these together, what you get is linear momentum. In linear momentum, mass is resisting the motion. If I'm massy, I tend to move more difficult. If I'm light, I can move easier. Velocity is something I have, maybe a force applied on me, and I gained the velocity that I move with. So mass is resisting, and velocity is making you move. So let's keep this analogy and consider angular momentum. What's angular momentum is very similar to the linear momentum, but angular momentum is the momentum of the rotation, rotational motion. In there, you have the moment of inertia instead of mass, and instead of linear velocity, you have the angular velocity. Now, very similar to mass times velocity in the linear momentum, you can express angular momentum as moment of inertia times the angular velocity. Now, if you somehow gain angular velocity with your own moment of inertia, you can have angular momentum. If nothing happens, you will spin because you have angular momentum around a fixed axis. Say you are a dervish, you are rotating. Now, if somehow you change your moment of inertia to conserve the angular momentum, something has to change to balance. Now, angular momentum is the multiplication of moment of inertia and the angular velocity. So multiplication has to stay constant. If somehow you, say, increase your moment of inertia or decrease, the angular velocity should act oppositely to conserve that the multiplication is a constant. Now, how can you change your moment of inertia? Moment of inertia, eylemsizlik momenti, is your tendency to not rotate, or how can you make it harder to rotate? Does any of you did any ice skating in your life? If you notice, well, just for experimental purpose, for physics purpose, next time you watch the ice skating competition, pay attention to those ice skaters when they close their arms, they tend to spin. Of course, it's nice and beautiful to watch, but when they want to spin fast, they tend to close their arms, or they do this. And to slow down, they open their arms. Because when you open your arms, you increase your moment of inertia, and your angular velocity has to decrease so that the multiplication should stay the same. Now, it's not practical to do the experiment on an ice skating ring. You can, but that ability requires some of practice. You cannot just jump on the ice and start spinning. But instead, you can sit on a stool that can rotate easily. You must have this in your dorm room or study room, unless if you have somewhere in the dental waiting room, you can play with it. When you sit there, spin, turn yourself, and then open your legs and arms. You will feel that you will slow down. And as soon as you close your arms and pull your legs back to your body, you will start rotating faster. And do the same thing over and over. What you will see, when you extend your arms and legs, you slow down. When you pull them towards your body, you rotate faster. Because when you do pull, you reduce your moment of inertia. That means your angular velocity has to increase to conserve the angular momentum. So do this experiment. If you experience the opposite, that means you found something. So you can come talk to your instructor and say that you destroyed the strong fundamental case of angular momentum conservation. But you have to do that experiment many times to confirm. One experience is not enough just to say something such a big impact. So that is the angular momentum conservation. Last time we have seen at the very end, the angular momentum conservation required an important fact. We expressed the system involving a star and a planet sweeping an area on a hypothetical plane on which the orbit of the planet is found. And we have seen that the area swept by the planet in equal times are equal. So today we will elaborate that as well, but not immediately. First, we are going to look at something very important. That is our today's topic. Now let's start with gravitation. What is gravitation? Does any of you know what gravitation is? To answer these questions correctly, you can read the chapter before you come to class next time. Not this one, but the next one, so that you will know what I will be asking you. They are all in your textbook. Does any of you heard of gravitation? Yes, maybe sometimes. But we didn't pay too much attention. Why do we have to? But now it's time to pay attention. Gravitation, or gravitational force, is one of the 4 fundamental forces of nature. Now, the whole nature that we are living in is governed, or mostly governed, by 4 fundamental forces. One of which is the gravitational force. Does any of you know the other 3? The other one is the electricity and magnetism, electromagnetic force, which you will study in the later stages of this course. And one other is the strong force. Again, you will study when you talk about the binding force of an atom. And there's the weak force that you are not going to study in this course, but you will see some areas that weak forces can apply. Now, today we are going to study one of the 4 fundamental forces of nature, the gravitational force. So, for the records, let's say gravitation is one of the 4, not many, fundamental. Everything works on these. And these are fundamental forces of nature, not just our city, not just our planet, the whole universe is governed by these 4 forces, or to most extent governed by these 4 forces. Now, this force, gravitational force, is the attractive force between large masses. Say here is M1, here is M2, which are distant from each other by r. Let's say this is our position vector. And the gravitational force on mass number 2 due to mass number 1 is towards mass number 1. It pulls, it attracts. And it's related to a constant, which we will see in a minute. The 2 masses, M1 and M2, divided by distance squared, distance between the 2 objects, in the direction of minus r, towards it. Now, here the gravitational constant, G, is a universal gravitational constant. It's 6.67 times 10 to minus 11 meter cubed second square and kilogram minus 1. Meter cubed over second squared over kilograms. Now, this force, gravitational force, is discovered by someone famous. You already know this person, and now you should tell me at least this name. Who discovered the gravitational force? Or who identified? Gravitational force has been there all the time, but somebody said there must be a force such and such that obeys, that it's related to the 2 masses that attract each other, and it has to be inversely proportional to the square of the distance between them. So who was this personality? It's Newton. You have already studied 3 laws of Newton, and this is an important discovery that he made. Gravitation was discovered or identified. As I say, it's not a discovery, it has been there, but somebody just said in a logical, understandable, physical manner. by Newton. Now, this gravitational force is a long-range force. And it's important between large masses. Now, according to this one, each one of you sitting in the classroom should attract each other through the gravitational force, because you have certain amount of mass, you are distant from each other. So each of you and each of these objects, this pen and you, this projector and you, should be experiencing gravitational force. You can determine how big is the gravitational force. Just multiply G, a constant right here, your mass of it, say 5, 10 kilograms, and the distance 4, 5, 6 meters. You will find that it's tiny. It's not that large. If you do this for large masses, you will see that it may be an effective force. Now, with this at hand, now let's consider something that we are more familiar with. Let's consider the sun, our energy source, although today it's predicted that you are not going to see the sun, but we know that it's somewhere there. It's bright outside. And here is the Earth. And these two are distant from each other at a certain distance. And Earth moves around the sun on an almost circular trajectory, where we are going to study this in detail. It moves at a constant speed, but constant speed with changing direction, meaning that the velocity is always changing, because velocity carries not only the magnitude and also the direction. If the direction of the Earth is changing, although its speed is not changing on a circular path, that means its velocity has to be changing. Now, as Earth rotates around the sun, it feels the gravitational acceleration. So there is the force of gravity, that is G, M1, M2, whatever, we will put it down. But now let's keep it aside and remember one thing that you have studied earlier. If an object, forget about Earth and the sun, if an object is moving on a circular path, it's not going in any direction, it's just moving on a circular path, it should feel a force. So, the force that the object feels is, or has to be expressed as, mass of the object, let's call it ME, times the acceleration. So if there is force, if there is mass, there has to be acceleration. An object is feeling this force, therefore there has to be associated acceleration. So what is this acceleration? NS101. What is this acceleration? Somebody should help your friend. You talk so much that you deserve every questions. You probably talk more than I do. Okay, do you have any answer?
Gravitational acceleration.
No. It's something other than gravitation. We keep gravitational acceleration or gravitational force aside. If something is moving on a circular path, it should feel a force. Now take a sling, move it, take a sling with a stone at the end and rotate it. If you cut the string, it will go in a straight direction. It won't be going around your head. Something is holding it there. Our Earth doesn't have to be just rotating unless it feels a force. Now, I don't know if you studied, of course. I presume that you studied this force. It's a wrong answer, but your intention is correct, but your answer is wrong. The answer your friend gave is merkez kaç, which is wrong, but something related. It has center in it. Centripetal. You see, you have the answer. That's why I asked you. It's the centripetal acceleration that an object feels if it's rotating on a circular path. So, Earth-Sun system is a system that attracts each other, and Earth is in motion around the Sun in an almost circular orbit. So Earth must be feeling the centripetal force, or related to the centripetal force, it must be feeling the centripetal acceleration. So if we identify that the acceleration here is the centripetal acceleration, then we can write that A here is simply V squared over R. That is the centripetal acceleration. The constant speed on a circular path divided by the radius of the circle. So that's why I indicated this V over there, which is a constant. Speed is constant, but the direction is always changing because it's a circle. It's pointing in a different direction all the time. Now, we remember what we put aside, the gravitational force. We know that there is the gravitational attraction between them. Let's call it, this is M sun. That has to be equal to the centripetal force. Now, this is an equation. We can simplify it a little bit and notice something striking. Earth rotates around the Sun with a force or a combination. Don't get lost there. But the mass of the Earth does not play any role in this whole business. You can solve this equation for, say, the speed of the Earth around the Sun, which is independent of its mass. It depends on the mass of the Sun, and it depends on the distance between the Sun and Earth. But it doesn't depend on the mass of Earth itself. So we have the relation once again, G m sun over r squared is v squared over r. Now you can express v squared over r in terms of angular speed, that is w squared times r, whichever you want to obtain. Now you can solve this relation for v and obtain something like this, gm sun over r, that is independent of the mass of Earth. So Earth is moving at a speed around the sun, but its own mass doesn't play any role in this business. What it is dependent on is the mass of the sun, what is attracting it there, and the distance from the sun. Now, there's more to learn from here. Now let's rewrite this G ms over r cubed is the angular speed, and that is equal to v squared over r squared. So we just played with this equation up here. What would this give us? Now let's take a look at this part, v. What is this v? Here is the sun, here is the Earth. It's in a circular trajectory around the sun with a radius of r. Can we determine this v if the speed is constant? Bu sefer konuşmuyorsun, sana yok. Kimse konuşmuyor, soru soracak kimse yok. So what is that v? Earth is moving around a circular trajectory. In a certain amount of time, we know that time. Do we know that time? How? It's 1 year. That's what we call a year. And can we determine the path length if it's a circular path? Yes. If we know the radius of this circle, it is just the circumference of this circle. Easy. Doesn't have to be too difficult to answer. So, we actually know this constant speed now. Because if the radius of this circle is r, then v has to be distance, that is 2 pi r, divided by p, period, 1 year. If you have to know the number, you can just convert it into seconds because it's in SI unit. But let's say P is the period of 1 revolution. Around the central object. So what we can do next is put this v in place of v squared here, g m sun over r cubed is equal to angular speed square. Sorry about that. But let's focus on this portion over here. V square is 2 pi r square over p whole thing squared divided by r squared. Now, if you take the square of this 2 pi r over p, you will find that r squared here and r squared there will cancel, and it will be equal to 4 pi squared divided by p squared, which is something with extreme importance. Now, we will express finally that if an object is revolving around a massive, bigger mass object on a circular path with a radius r, there is a balance between g, universal gravitational constant, the mass of the central object over r cubed is equal to 4 pi squared, a constant, divided by p squared, the square of the period of one revolution. You will soon see that this is sometimes called Kepler's third law, but we don't identify it yet with that name. Now, take the sun out and put any two objects, one moving around the other one on a circular path. Then, of course, you would generalize this for any object, not only sun, earth. This was our example today, the way we proceeded. But for any object, M1, another one, M2, that is moving on a circular path with a constant speed, and the circular path has a radius, say r, you can write that g m1 over r cubed is equal to 4 pi squared over p squared, where p now is the period of one revolution of m2 around m1 on a circular path. So it doesn't have to be just Earth and Sun. It can be any object. And that makes what we will see, Kepler's third law, applicable to any objects which perform similar motion. Now, once again, we should emphasize here that this whole thing is not dependent on the mass of the object that we are trying to understand better. Here we use its period of revolution. This is the distance from it, and it doesn't depend on its mass. One important thing to note, that if we go back to here, we did something very important. We equated two forces. This one is the gravitational force. The other one is the centripetal force, but F equals ma is just Newton's second law. So here, what we have is what's called inertial mass. And what we have here in the gravitational force, the gravitational mass. And at this point here, we see that they cancel each other. They are the same. Inertial mass and gravitational mass are both the same. Any questions? Now, in the last few minutes before the break, let's remember the three famous laws of Kepler, which are identified empirically based on observations. This derivation that we are going to see closely later, but here it is, Kepler's third law, was not formulated in this form by Kepler. Kepler came up with this empirically, just to explain the observations. Now, the first law of Kepler is that planets move around the sun in elliptical orbits. I'm sure all of you know what's ellipse. You must have seen it. It looks like a circle, but it's sort of pulled circle. It's indeed a pulled circle. A circle is a special condition case of an ellipse. Ellipse is more general. Ellipse can be very elliptic or close to a circle. Circle is a form of ellipse in which its eccentricity, being elliptical, is a certain number. What number? I'm not going to ask now. I'll ask in the second hour. It's in your book. You should take a look at it from time to time. Now, the first law of Kepler states that planets move around the sun in elliptical orbits with the sun at one of the focus of the ellipse. Now, a circle has a center, an ellipse has two foci, two focal points. When an ellipse tends to become a circle, the two focal points overlap so that there is only a center. So here's an ellipse. There is the planet moving on elliptical orbit around the sun, and the sun is at one of the two focal points right here. The other focal point is right there. So this is Kepler number 1. 2 is what we already know, that the line, the hypothetical line, there is no line between a planet and the sun, but we will say the line connecting a planet and the sun sweeps equal areas in equal times, in equal duration of times. Now what this is here is the elliptical orbit again. Here is the sun at one of the focal points. Here is the planet. Now, planet moves around this elliptical orbit around the sun. Let's make it bigger. And if you were to connect the two with a line, and just pay attention to this line as the planet moves around the sun, it sweeps an area. Say in 1 month, it goes from here to there. Now the planet is here, and it swept an area, let's call it A1, in a time of delta t. Now sometime later, say in 6 months, the planet is here, and in 1 month it's going to move to somewhere, and you will see that the area swept by the line that connects the planet and the sun, let's call it A2, here is A1, and here is A2, in delta t, you will find out that A1 is equal to A2. Why do I say we already know this? Is something you all should remember. Because I explained it to you. We have seen last time that we expressed angular momentum in terms of area swept. And we have seen that angular momentum is a constant. Therefore, dA over dt, the area swept in time, is constant. That means the planet should be sweeping the same area in the same amount of time. And this is it. This is Kepler's second law, which comes from the angular momentum conservation. So where it's coming from? Not yet, not quite, angular momentum conservation. That's important. So next time you answer correctly. So we know already that this is angular momentum conservation. So let me ask you another question. We are already out of time for this hour. Now, do we experience such a behavior in our solar system? Earth moves around the sun on an elliptical orbit. It's not an ellipse, it's almost a circle, but it's an ellipse. You can feel how elliptic it is from one simple fact. Now, Earth has to be moving faster and slower at some certain parts of its orbit. When it's close to the sun, it should be going faster. When it's on the other side, it should be going a little slower. Do you feel such a thing? Do you feel at all that Earth is moving? Well, you should be feeling, because the seasons are changing. Sometimes we have the summer, sometimes winter, because of the angle of inclination. Of course, not because of the distance to the sun. But you know, you feel the difference between being close to the sun and being far away from the sun. Now let me ask you the question in a different manner. Did you ever wonder why February is 28 or 29 days, while 6 months ahead, August is 31 days? Did you ever ask yourself or your parents, why did they make February a little shorter? Just because they don't like February? No, because in winter time, in the northern hemisphere where we live, we are feeling the winter, fine, but winter summer is because of the sun angle, not because of being close to the sun. In winter time, in fact, we are closer to the sun. We are close and we are moving fast. So we make a quick turnaround. It goes a little faster. How fast? 2 days in 180 days. And then summertime, when the Earth is further away, relatively, it goes a little slower. It takes longer to cover. So that's why on an elliptical orbit, the winter is a little shorter, the summer is a little longer, as we feel on the northern hemisphere. People on the southern hemisphere feel exact opposite thing, because seasons are governed by the angle of solar light. But here, being on an elliptical orbit makes that slight difference. Now, you can tell that if there was no difference between summer and winter, then the orbit would be a perfect circle. But there is a difference. What is the difference? 2 days in 180 days. So you can see that it's not a circle, but very close, 1 over 180 or 1 over 90. 1 in 100 is how far we are roughly away from a circle.